Thanks, Paulo. So today's lecture is on a topic called introspection. A little bit of overview. So I'll begin with a very brief overview of introspection in AI. It's a topic that has been addressed from pretty different perspectives, but I think it's a good context to have. Then the two main parts of the lecture will be introspective convolutional neural networks, where before going on to the ICN model itself, which dates from a few years ago, we'll discuss a few building blocks, or what I call building blocks, for introspection in machine learning. Then a little bit of the overview of the approach and some empirical results. And then I will be closing today's lecture on a topic that applies concept induction, which is something pretty similar to inductive logic programming. It could be thought of in that sense, but focused on ontology languages, specifically description logic. So I'll be covering a work on human compatible explainable AI. Right, so the first part is a very, very brief overview of introspection throughout the years in AI. So to begin with, the term itself, introspection, is not a very well-defined one in AI. One use since the very early days of AI, way back in the 50s, seeks to equip systems with some sort of process, like heuristics. For us, it's now the term heuristics is a pretty well-known one for when you want to have some sort of approximation algorithm, something that generally works well but does not provide any guarantees of success, that are based on human problem solving. So some of the precursors back in the 50s, Newell and Simon's general problem solver, which explicitly was based on intuitions about how humans address and try to solve problems. And they, in those early days, they developed a lot of examples by hand to try and mimic them automatically and algorithmically. Then there was about 30 years later, in the 80s, Lenat's automated mathematician, which also sought to make mathematical conjectures, kind of like the abduction-based material that Paulo covered last time, based on heuristics, also followed by human mathematicians. And then a book by Douglas Hofstadter, which is a cognitive scientist. I'll come back to him in a little bit later. He published this book called Fluid Concepts and Creative Analogies, Computer Models of the Fundamental Mechanisms of Thought. That was in the second half of the 90s. That sought to cover AI systems that serve as cognitive models for a variety of toy examples, but that were significant examples of how humans carry out their reasoning processes. So there's another book by this same author. So it's actually a Pulitzer Prize winning book from 1979. So this kind of a philosopher, cognitive scientist, Douglas Hofstadter, called Gödel, Escher, and Bach. If you haven't read this book, I really recommend it. It's an excellent example of the interest at the time related to AI and cognition, but it's also, in my opinion at least, a must-read for anyone who's interested in all of these topics, all the relation between consciousness, cognition, logic, math, artificial intelligence. More on the symbolic side, of course, but I think it's a really interesting book. And then, while preparing this lecture, I ran into this much shorter, just a short article by the same author in The Atlantic called Gödel, Escher, and Bach and AI, that I'll come back to in a few slides, which provides a pretty interesting perspective on generative models, specifically ChatGPT. So going back to the general vein of introspection in AI, I found this also another article, which is linked down here by a researcher called Roger Gross, that provides a pretty interesting analysis saying that, so it's almost from 10 years ago. So he was saying already at that time that the general view that I was just talking about of introspection has kind of lost appeal in the mainstream approaches in AI, and the development of intelligent systems in general. And that he claims that the field has kind of like a behaviorist-like aversion to thinking about algorithms in terms of plausible mental representations and cognitive strategies. On a personal note, I think this is related to, so when he wrote this article, it was 2013, it was, I guess, the rise of deep learning. So, it was kind of winning out over these more symbolic approaches to implementing or deriving cognitive capabilities in intelligent systems. And he claims that there are several arguments against introspection. That's why, he's trying to explain why this loss of appeal happened. And he claims that we kind of already have rough outlines of a solution for most of the problems we're interested in. This is a pretty, bold claim, but that introspection itself won't help us fill in any of the details, and that computers have been shown to be different enough computational architecture different from our brain that we can't expect any insights really to carry over. This, in my opinion, is a pretty open problem still. We really don't know exactly how the brain works, but it is a pretty different architecture from at least the ones that we have so far. And it isn't scientific. So the way they were tackling the problem of introspection, it isn't scientific, since different people often will disagree. So explanations are likely just somebody's idealized story about what's actually a much messier process. And it's also hard to predict what range of problems and introspection-based strategy will generalize to. So I guess as the upshot of this argument is that perhaps they were the path that research and development in this area was taking was a bit too general. So continuing with his analysis, he says, like any source of intuition, introspection can be seen as a starting point. It's not a rigorous scientific argument or methodology, but it ultimately needs to be backed up with experiments or with theoretical analyses that can provide guarantees. And what we really want with this kind of work is an explanation for heuristics that people use. So in other words, figure out these 4 steps, figure out what regularities our heuristics are exploiting. So what as humans we have picked up on, like the kind of structure that problems might have. See if any existing algorithms that we already have exploit these same regularities. If not, come up with one that does, and then move on to justify it theoretically and empirically. So he calls this kind of like an inverse Bayesian optimization, where through human observation we might be able to pick up on insights, algorithmic insights, or little bits of knowledge, procedural knowledge at least, that might help us out. So moving more to the topic of this course, introspection and neurosymbolic AI, I think that given the relative strengths that we have in machine learning and KR-based approaches to AI, introspection really is an interesting topic for NESI, neurosymbolic AI. So in this context, I put forward a definition that I just came up with myself. This is not a well established thing, but it's a pretty general definition saying that introspection can be thought of as a set of techniques that equip models with tools that allow them to elaborate on their own results. So we also have seen this in speaking of ChatGPT and LLMs in general. We've seen work called reflection, so like self-reflection, trying to question itself. And I think this sort of technique it can be very powerful. So in this lecture, as I pointed out in the overview, I selected a couple of approaches, one based on machine learning and the other one that comes more from the KR side, but works with machine learning models. All right, so starting with the first one, ICN, Introspective Convolutional Neural Networks. This is work from 2017 that we'll be going over. But before going into the details, I want to review two techniques that are important to the model that I call the precursors or building blocks for introspection in this, at least this sub track or sub path of introspection. The first one is generative models. I think we've seen a lot of this kind of work in the past decade or so, even more. And then also semi and self-supervised machine learning, which is also pretty interesting technique that has also been around for quite some time. And I call them building blocks for introspection because I think they're important steps in developing this kind of features that I've been talking about specifically in machine learning models. All right, so first of all, what's a generative model in comparison to what a discriminative model is? It's pretty common to see references to generative models but no, there are, at least in my experience, coming more personally from the KR side of things, there aren't a lot of clear explanations on what generative models are actually after. So it's commonly assumed to be something that's everybody knows, and at least in my case, I haven't seen clear explanations. So I went out and looked for them and built a few introductory slides to share. The first one, discriminative models are the most common ones, at least in classification. I'm talking in the realm of classification tasks. Discriminative models are pretty simple. They seek to establish what's called a decision boundary to separate classes of interest. So here we see, green dots belonging to dogs, blue dots belonging to cats. They're not involved. They don't seek to actually describe the elements or the classes themselves. They just say, from this point on, like over to that side of the space, you have class A, and on the other side you have class B, and that's all they want. So to discriminate between two or more classes. Generative models, again, for classification, all generative models build probability distributions based on the classes and features. So they, in comparison to discriminative models, they do provide information regarding the contents of each class. In particular, what's interesting is this capability here. So they have, once you have what was learned from the model, which is a probability distribution, you can sample from those probability distributions and thus generate elements. So that's where the name comes from. You can generate elements based on the probability distribution. So this, in particular, this figure isn't that helpful in the sense that, it's not quite clear what it's conveying. It's just, carving out part of the space and saying, here are the dogs and here are different kinds of dogs and or cats, but it's not conveying specifically what's going on. So I like this graph a little bit better. This this illustration because you can see exactly what's going on with the goal. So you're trying to here directly estimate the probability that some unseen data will belong to one of the two classes. So you're saying, what's the probability of my observation given that it's in class A or class B? And examples are typical things like SVMs or regression based classification, where generative models, they estimate a probability distribution to deduce the same thing that the decision boundary was giving you before. So what you're learning, instead of learning this boundary, you're actually learning the probability distributions of the data. One of the most well-known techniques for this is naive Bayes, of course, where you end up learning a probability distribution, and then you can use it for the same kind of task here, but you can also generate elements based on these distributions. So this assumes, generative models assume that the world behaves kind of like this. So that there's some sort of true model provided, by the world. This is what we're trying to learn. And then what you come up with is a data generating process that then you can just use to generate data. So it's often useful in AI and data science to think about the world in this way. So the true model is the phenomenon that you're investigating, that you hope to understand, and then the data generating process is comprised of real world mechanisms that create the data. So and you can record if you want, and that is precisely what generative models seek to learn. There are two pretty well-known examples that we'll be illustrating here. The first one is Markov chains. So you've probably run into this model. I have in another window here, an illustration of this actually in a dynamic example. So Markov chains, they're essentially sequences of random variables that describe some sort of dynamic process. So in this case, you can see, you can move speed here, you can make it faster or slower, but you can see that the system is going between two states. So it can either stay in state A or transition to state B, or the same thing symmetrically. So what I wanted to show you here is, if you want, you can change the probability. So if you want it to be the most probable thing is for the system to stay in state A, you can see that there's a 10% chance of transitioning, and you can do the same thing here. So what's interesting about this is that they can model, so if these states were rainy or sunny for weather, is you can simulate this, and that is actually a Markov chain used as a data generating process. So we can see here that what we're sampling is actually from this process. So this is generating data based on the process. Here you can see the S's that are being generated, and then the rain, the sun. So I think it's a pretty interesting way to actually see these things working. So if you want to play with this, you'll have the link in the slides. The other one is, of course, much more well known. I think, well, not, I don't know if much more, but it's a more of a generative model called generative adversarial networks, or GANs. So these were developed several years ago and have shown a lot of applications in the real world domains. And the way they work is that they're divided into two models. One is a generator, so you can have random. It's uses random input, so kind of like random noise to work with this. It generates what's called fake examples because they're trying to compete with actual real world examples that you would use for training. And then you have the discriminator, which tries to see if they can discriminate between real examples and the fake ones that are being generated. So in this case, it just says, you know, real versus fake, and then based on this performance, the generator will try and adjust its performance. I also have so this is an animation of what's going on. We're going to see this working in a second. So it's trying to sample. The purple ones are fake samples, and the green ones are the real ones. And you can see how it adapts. So this is just a short animation, seeing how it eventually gets much closer. But we can also go back here and see. Let's refresh this. And you can play with, you can select the distribution that you want to learn. So either you have this straight line, two kind of blobs, the ring, or just a few, you know, different spots of data there. So let's go with the ring. I think it's a pretty interesting one. And then here, if you click here, you can also make the generator have more neurons. It'll be a little bit more capable. I think it works better if it has more neurons. And then if you make it run, so you'll see that the purple dots are being sampled, trying to imitate the target distribution, but all they have to work with is a loss function based on how well the discriminator is being able to detect real versus fake. So the discriminator is trained already with the real data, and the generator is trying to fool it. Here, this visualization is also showing you the points where the gradients are. So this point here needs to move that way to be closer to performing better. So this is pretty slow. So it's running locally, I believe, and it doesn't always work. Doesn't always reach the best result very quickly. But I think it's a really nice thing to play with and to illustrate what's going on. And again, you can change a lot of the optimizers, learning rates, different kinds of noise here. So I think it's a pretty interesting tool. All right. So that's the GAN lab. So generative models, of course, we've probably all seen these kinds of applications. So these are random images. I think this comes from those websites. This something does not exist. In this case, it's this beach does not exist. These are random images generated by generative models, basically saying, generate me some beach, and in general, they work very well in certain domains, not so well with human hands. In that case, we've seen a lot of limitations in that sense, but they are getting better. So they are pretty powerful. Other examples are audio being generated here in this case, I think based on, I think the top one is from, I think it's Meta or Microsoft, I'm not sure, but it's based on textual input. It generates different musical beats and melodies and that kind of thing. Of course, ChatGPT or the GPT 3, 4 tools, and also I think this is Adobe, where you can edit images basically with prompts and generative fills and that kind of thing. So this goes way beyond the very simple things that I was just showing you. Just wanted to show you how powerful they are for certain applications. But going back to the author of this book that I was telling you about, and these comments by the author. So he was discussing in this article this experience he had where I don't know why some person was trying to use ChatGPT to essentially impersonate him and saying why he wrote the original book, and the person sent him this and said, hey, can I publish this? Are you okay? And he was frankly appalled. He was saying that it didn't sound anything like him, that it was just some fluffy hand waving kind of thing, even though it sounded very well to the random reader that didn't know what Hofstadter sounds like. So, but I liked a couple of quotes here saying, well, I'm frankly baffled by the allure for so many unquestionably insightful people, including many friends, of letting opaque computational systems perform intellectual tasks for them. Of course, it makes sense to let a computer do obviously mechanical tasks such as computations, but when it comes to using language in a sensitive manner and talking about real life situations where distinction between truth and falsity and between genuineness and fakeness is absolutely crucial, to me it makes no sense whatsoever to let the artificial voice of a chatbot chatting randomly away at dazzling speed replace the far slower but authentic and reflective voice of a thinking, living human being. So I highlighted a few of the terms here. I like this real life situations where you have to distinguish between truth and falsity. I think this is one of the crucial limitations of these models, where they're just training to be able to repeat what they've seen in the training data, and they really have no grounding, and that's why I'm making such a point here in this lecture. There's no grounding with any actual notion of truth in the world. So they're just essentially parroting away, based on these distributions, where it works really well for things like, generate a beach or something that has no impact on the ground truth of the world. But when you want to actually ask them about something, it often makes a lot of mistakes. So the second one is to fall for the illusion that computational systems who have never had a single experience in the real world outside of text are nevertheless perfectly reliable authorities about the world at large is a deep mistake. And he warns, if that mistake is repeated sufficiently often and comes to be widely accepted, it will undermine the very nature of truth on which our society, I mean all of human society, is based. So it's pretty intense what he's saying, but I think he's right in the sense that you really have to treat these models as being very useful for certain things, like I was just saying, but for others, they're really, frankly, out of their depth. We'll be using them, of course, very responsibly, as we'll see in a minute. The second building block is kind of like an intermediate between the well-known techniques of supervised and unsupervised learning. So semi-supervised learning combines or seeks to combine in certain situations the best of both worlds by making use of a small set of labels and then iterating. And we'll see that this is at the heart of what we're both building blocks are going to be at the heart of the ICN model that we're building towards. So you can see them as why is it the best of both worlds? Because unlike unsupervised learning, it can be applied to more problems, essentially, from classification and regression to clustering and association. So unsupervised learning is typically relegated to things like clustering. So on the other side, unlike supervised learning, which uses assumes that all the data that you have is labeled, it uses small amounts of labeled data and large amounts of unlabeled data. So it kind of balances out in that sense, reducing the effort spent on manual annotation that is expensive typically because it comes from humans annotating ground truth, and also cuts, of course, data preparation time. And self-supervised learning is a specific type of semi-supervised learning that we'll see in a minute. So supervised learning, you can see the semi-supervised learning versus both worlds. So it kind of sits in the middle, right? So supervised assumes that all data is labeled and you get your model. Unsupervised assumes that all data is unlabeled and you get your model. And here you have this combination that I was just talking about. Semi-supervised self-training is pretty interesting because first you obtain your first classifier with a small portion of labeled data, and then you use the unlabeled data to classify based on that model, and then you get what's called pseudo-labeled data. And then you get you take a selection of the most confident pseudo-labels and the original labeled data, and then you get your improved classifier to get your predictions. So this is what's typically called self-supervised or self-trained. So this is another one called co-training, where you can also establish, interacting training procedures where you can typically get your most confident predictions from one classifier and use it to label in the other. So it's a way of again trying to get the best of both worlds. So we finally arrived at the model that we wanted to see in this lecture, which is introspective convolutional networks. So the authors in this case were motivated by these observations that even modern classifiers like deep neural networks still make mistakes that look absurd to humans. So they're very, very good. They even have superhuman capabilities in a lot of classification tasks, but then they also make these kind of stupid mistakes. So one common way to improve classification performance is by using more data, of course, but in particular, the hard examples. So where are they making mistakes? Essentially trying to learn from their mistakes. And there have been a lot of approaches up to the proposal of this model where you kind of try and do that, like learn from your mistakes. Bootstrapping is a pretty well-known one, active learning, semi-supervised learning that I just went over, and data augmentation. But in this case, in all these cases, all such approaches use data samples that are either already present in the given training data, or like active learning, assume that they can be additionally created by humans or separate algorithms. So their proposal was to improve CNNs by giving them synthesis capabilities to make them internally generative. So this is what the proposal that makes them introspective, essentially. So this is the overview of the approach. We're going to go over each of the stages in a minute, but you can see that it's one model, it's end-to-end, and at the middle they have this introspective neural network where it begins by classifying, it's given this challenge of a data set, and the initial decision boundary is here, and then it'll iteratively try and sample where it goes wrong and auto adjust. So in the middle, again, we have it's simply it's the same algorithm for training a convolutional neural network. We'll see this in a bit, and then it'll synthesize what they call, what this actually comes from, this term comes from a work 10 years ago, 10 years prior to this one, that we'll see also in a bit, called pseudo-negative samples, where they also try to learn the ones that they're making errors on, essentially. So, and on the other side, you have your what's called the reclassification step, where it'll iteratively also try and refine this initial decision boundary based on adjustments from the pseudo-negatives that they sample. And we'll see this in a bit with real-world data. That's pretty interesting, what they come up with. So the main algorithm, essentially what the heart of the paper is doing is all in this slide. We'll go over it briefly to see the main points. So essentially, initially, you're giving a set of training data as usual. You obtain a reference distribution. You train an initial CNN binary classifier. And this is essentially what's going on here. You have your initial classification, your initial decision boundary saying, okay, the blue dots are from the purple line down, and the red dots are up. The synthesis step is based on sampling these pseudo-negatives from the current model. They propose using a stochastic gradient descent sampling procedure. They say that it's pretty efficient, and then they augment the pseudo-negative set with the new samples, essentially. So what's going on is that based on this, essentially at the first step at least, they're sampling this. So trying to come up with samples that are on the negative side of the classification task. And then the reclassification essentially updates the CNN classifier to the one in the next step, essentially based on this. So now they're updating this initial very, very basic decision boundary, saying, all right, I'm trying to cut out these negative samples that I found. So it, as a first iteration, it's already looking much better. So using this to inform the process. This is going to happen for, I don't know why they wrote it as a for, in this case, a for loop, where actually what they're doing is doing this until convergence. So in the paper, they prove that it's guaranteed to converge. So there's no improvement on a validation set. So essentially, it's going to run until this condition holds. So this is shown to always hold. This is what I wanted to get to, because I think it's very interesting. This is for the MNIST data with the ICN classifier. So the training data, of course, is the well-known data set on digits. So you have 10 classes from 0 to 9. You have a few different examples of each. But what's interesting, what's going on here is that, so this is going from the first iteration up. First, you can essentially see that it's just noise at the beginning. You can see a little bit of the texture of the zeros, but as it progresses, it gets iteratively closer to zeros. But what's interesting, if you look at the after 35 training stages, iterations, you can see that, remember that these samples are the pseudo negatives. So they're trying to see what looks like a zero but really isn't. So in this case, zero isn't that clear. But if you look at the ones, you can see what, some people might write ones with this little edge here in the bottom that kind of looks like a 4. It might be mistaken with a 4. So as negative examples, it generates those kinds of images, which I think is pretty interesting. The same thing with the 2s. You have this loop that might confuse the classifier and make it seem like a 3. The 3s themselves, I'm not sure exactly what's going on. Maybe they kind of looks like a 5. And I just chose 0 through 3 here to zoom in, but you can also look at others, like the 4s. If you look at the 4s here, you can see that they're the ones that kind of close on top, and the same thing with all the others. The 7 is also interesting with the crossed section here, which is not part of the data set. So yeah, that's pretty interesting what's going on there. So then they also compared with other, so they have 2 different ways of classifying. They do one versus all for MNIST, which is a 10 class classification task. They do either a one versus all or a softmax approach, which is a typical way of doing, and then comparing different approaches. And the ICN is the one with the lowest metric for error. Here they're comparing sampling strategies. So they have SGD, different types of SGD, with early stopping, I think, is the option 1, and the other one is a different algorithm. And yeah, so they have different types of sampling strategies, and they're also seeing that it's generally softmax works better in this case than one versus all. In this case, this experiment, they're trying to see the effects on varying training sizes, which I think is one of the advantages of this model. So CNN and the ICN with noise are taken as baselines, but the ICN algorithm is already, so the testing error is already much lower with small training sizes than the others. So it makes better use of the data, I guess, is the conclusion. When after 55,000, they're similar, but they make better use of the data. So this is for testing error with different against different approaches. So let me remember what's going on here. Without data augmentation, with data augmentation. In this case, also with the CFAR data set, and they're producing competitive results also against all the other models, but data augmentation has a significant impact on all models. So the other data set that is it's much more difficult, the house numbers data set. It's more like a real world, less curated data set, and they also they're not significantly better, but they do provide competitive results. And again, these are the original experiments from 2017. So there's a closely related model that the authors themselves say that they were the inspiration that they use it as an inspiration for their model, which is called Generative via Discriminative Learning, or GDL, that is from 2007. And if you look at the general pipeline, it is pretty similar. So what they're doing is they have a target distribution, they have iteratively refined discriminative models, also based on pseudo-negatives. This is where the term comes from. And you can see here how they start forming this this cloud of pseudo-negatives, and they use it to inform and refine their model until they learn their final iteration. So the authors analyze this and saying, okay, yeah, it is a similar pipeline, but there are differences. So the first one is that GDL is based on boosting. So it's a different technique. Instead of applying neural networks, they're just sampling based on the probability distribution. ICN focuses on supervised classification tasks, whereas GDL was originally at least conceived as generative modeling, and classification was not addressed. So it's more specific. ICN is more specific for classification. The sampling strategies used, so I mentioned this briefly, the authors of the ICN model use stochastic gradient descent, whereas GDL uses Gibbs sampling, which is based on what we saw before for Markov chains, and it is more efficient. So this synthesis through backpropagation has shown to be really much more efficient, and it converges much faster. I think this is one of the main differences: a single CNN versus a cascade of classifiers. So the ICN model maintains a single model, a single classifier, whereas GDL is essentially a sequence of classifiers refined via boosting. And also this other one where ICN has greater representational power because it's an end-to-end training technique for CNNs, whereas GDL relies on manually designed features. So I think this is also where it distinguishes itself. The other thing that you might be thinking is generative adversarial networks that we looked at earlier in this lecture, where in the introspective nature, I think, is what distinguishes it in this sense. So ICN emphasizes being introspective by synthesizing samples from its own classifier, whereas the GAN model, as we saw, implements two distinct networks, one acting as a discriminator and the other one as a generator. Again, this supervised versus unsupervised. So the main focus of ICN is to develop a classifier with introspection, where the GAN model seeks to build high quality generative models under unsupervised learning. So again, the same thing as before, where ICN is focused more on classification. And again, the single versus separate models. The ICN model is a CNN that is a discriminator and a generator simultaneously, whereas the GAN maintains two models. There are a couple of more differences. The reclassification by synthesis, which is what ICN applies, is quite different from Minimax. So ICN engages in this iterative procedure, which is called reclassification by synthesis, based on Bayesian theory, basically Bayesian updating, whereas GAN optimizes a Minimax objective function. And what's interesting about ICN is that it's the same training mechanism as that of a standard CNN. And finally, the multi-class formulation, in GANs, is they have to add an additional class called not real to the standard K classes, which results in additional model parameters, whereas ICN aims to directly learn the classification task by maintaining the same classes, the same parameter settings, without adding additional parameters. So that's the end of ICN. So in this final part of the lecture, I want to focus on this other work called Introspection via concept induction. So concept induction, to provide a brief definition, relies on what's called background knowledge that is assumed to come in a description logic ontology. So it has an ontology O with a terminological, so the rules that they have are in set T, and A box, which is the assertional part, or the database, the set of facts A. And they further assume that they're given two sets, P and N, consisting of individuals from the ontology. And P is essentially the set of positive examples, and N is the set of negative examples. And what the concept induction task is looking to accomplish is to identify complex or sufficiently complex description logic expressions that are modeled by the ontology for all the individuals in the positive examples, and are not modeled for all the individuals in the negative examples. So it might be the case that no such expression exists, because maybe there's no guarantee that that will happen. But then in that case, it's expected that the system will return some sort of approximate solution with some accuracy value. So as you might imagine, as I was saying, with the relationship between this and inductive logic programming, it's typically computationally very expensive or even intractable. So there's another set of techniques called concept refinement that approximates these expressions, and they are typically adopted for this for these types of problems. So what the authors of this paper focused on was applying this to generate explanations for humans, essentially, of machine learning classifications. So they're trying to provide explanations that will help humans determine understand why certain things are being classified as they are, or why mistakes are being made. So what we're going to focus on now is essentially concept induction together with a class hierarchy as background knowledge. As we'll see, they used a Wikipedia data set that first they want to generate explanations for data differences that are going to be meaningful for human observers. So they're going to show them images and saying, can I explain how these images are different? And for this, they used a prior work that you have here from 2019 called Efficient Concept Induction from Individuals. And they use this for generating explanations. So there's a heuristic on which this SE system relies on, that is essentially using only a class hierarchy as an ontology rather than a more complex one. This makes it much more tractable. And a limited search space for candidate concept expressions, so they're not exploring the full space, and some a priori materialization of logical consequences, so they don't have that bottleneck either. So they can perform concept induction over data sets that cannot otherwise be dealt with because they're too large, as we will see in a bit. And experiments have shown in their prior work that accuracy is still pretty high, pretty competitive. So as background knowledge, as I was saying, they used the Wikipedia knowledge graph, which is produced by retrieving the complete category hierarchy. We'll see a few screenshots in a bit. This is a crowdsourced data set, so it can actually contain cycles, which doesn't make sense. So if you have cycles like in a subclass kind of relation, it doesn't make sense, and you have to somehow break them, because otherwise that part of the hierarchy wouldn't make sense, and you wouldn't be able to use it. So they devised an algorithm for breaking cycles, and what the resulting data set has around 1.8 million concepts and over 6 million individuals. So this is a pretty large data set. So for the Wikipedia URLs are the individuals that are assigned classes according to the categorizations found in Wikipedia. So what they're going to do is something like this. So have images plus the knowledge graph, have this inductive logic programming system or concept induction system, where they're trying to look at expressions like this. This is from the original the data set paper. That's why they're talking about inductive logic programming instead of concept induction. So the Wikipedia knowledge graph looks kind of like this. So you have different categories of data, and then you have things like the subclasses of so engineering here is a subclass of the topic classification, which is a subclass of the OWL category of thing, which captures everything. So a little bit more in detail, you have thing that captures everything. You have things like inventors by nationality, and American inventors is a subclass of that, and Albert Einstein is an individual in that class, and also an individual in the class of German Nobel laureates. So in the first experiment, the goal of the authors was to assess the perceived quality of the explanations generated by the SC algorithm compared to both the gold standard, which is the human-generated explanations, and also they devised a way of coming up with what they called semi-random explanations, which if they were saying, in the paper they analyzed the situation where if you come up with completely random explanations, they're too easy to spot. So they devised a way of coming up with explanations that could be plausible, but they're not quite right. So the explanations themselves consist of brief textual explanations. We'll see an example in a bit of conceptual differences between two sets of images corresponding to categories. So they have category A and category B. So in this first example, in the first experiment, the two image sets, even though they represent the decision outputs of a binary scene classification algorithm, it's only hypothetical, because in this case, they're only trying to assess the ability of the algorithm to explain data differentials per se. So they're setting it up as if it were a scene classification output, but it's actually not. So this is what it looks like. The task is saying which of these better represents what the images in group A have that the images in group B do not. So there's the explanation that says just essentially a sequence of categories or individuals, like bakery, bread, indoor products, store, woman, or basket, bread, cake, ceiling, floor, person, wall. So in this case, it's the one on the left is human generated, and the one on the right is the one produced by the algorithm. So the both the human generated explanations as well as all of the evaluations were carried out with people that were crowdsourced through the Amazon Mechanical Turk platform. So the results, it was pretty clear that the human explanations were much better than the ones produced by the algorithm, but it was also clear that the random explanations were also not very good. So the explanations produced by the algorithm were much better than the random. So they do have explanatory power. There's also a lot of variability in SC's performance across the image set. So the authors point out that in some cases, the explanations were actually sometimes even winning out over the human ones, but also losing sometimes to the random ones. So there was a lot of variability there. In the second experiment, the authors were seeking to identify errors made by a machine learning classifier. And in this case, the goal was then to obtain an objective measure of the utility of the explanations in helping human users evaluate the decisions of an actual system. So in this case, they have a logistic regression algorithm for classifying images into scene categories. So based on semantic tags that basically referring to objects in images. And again, the goal was to test how well these explanations compared to human ones. In this case, they didn't have any random ones, helped human participants identify errors made by classifiers. So they have 16 image sets. There's also a crowdsourced, crowd-generated, noisy data set with objects and categories. And the categories were the ones that we see here, pretty, everyday stuff like kinds of rooms, kinds of buildings, places, different sorts of settings. So the images were fed then to the classifier, and then to classify them into either target or non-target categories based on their tags. And then the outputs, the classifier outputs a binary decision essentially as to whether the image is part of the target set or not. And then they were grouped according to if they were either true positive, true negative, or false positive or false negative as usual. And then they generated human explanations and also explanations with the same algorithm as before. So in this case, we have the task looks like this. Which group of images do you think this explanation refers to? And they give the explanation. And, it's also a sequence of terms, essentially. And in this case, it's referring to group B because it's referring to people, chairs, tableware, things that are manufacturing is going on here. And if you look at these images, it's not quite as related. So the authors, they generated 4 image sets to try and compare these 4 classes. So false positive versus true negatives, true positive versus false negatives, true positive versus false positive, and false negative versus true negative. They claimed that these were the ones that were more essentially more relevant to distinguish, to more like to have explainable differences essentially. So they looked into concreteness, which based on work from essentially natural language processing, there are metrics on concreteness to try and measure, given an explanation, how concrete you're being. And in an initial analysis, it was confirmed that the artificial explanations were noticeably less concrete. So they adjusted it, basically eliminating the ones that didn't surpass a certain concreteness score. So here we have before adjustment and after adjustment. You can see that the red ones are the ones produced by the algorithm, and before and after, you can see that the concreteness is quite it's much better, much closer to the ones for the humans. So this is for each different task. They also looked at discriminability, essentially trying to see if there was a difference in performance given the explanations, and this is based on choosing the one that maximized F1 or precision or recall. So you can see that there's a pretty important difference between the different tasks. Here we have also the estimates of discriminability, essentially, and bias. They also looked at bias to see if there was a tendency to return essentially an answer saying biased towards one class or not. And let me move over because I'm running out of time. Graphically, you can see that the SC generated explanations, I'm highlighting here the axes because they're different. The axes are in different scale, and you can see that the human explanations are have much more discriminability than the SC ones, but even the ones generated by the algorithm had a non-trivial level of discriminability. So jumping to the results, the human generated explanations yielded higher, as we were just seeing, discriminability for all four comparisons. But for both groups, there was non-zero discriminability. So this, even though of course it's not as effective as humans, there is evidence that it was an effective intervention across all comparisons. And they did, speaking of bias, they did observe that there was a bias towards responding for set A, which was consistently stronger even for the human-generated explanations. So this might be some sort of artifact of the experimental setup itself. So in conclusion, introspection takes and has taken throughout the years many forms in AI. Historically, as we saw, it began as an attempt to transfer human capabilities to artificial intelligence systems. From my point of view, it's arising as an important concept in neurosymbolic AI. So I think it lies at the heart of so the neurosymbolic AI lies at the heart of the combination of symbolic and sub-symbolic methods. And here in this lecture, we just chose two approaches. There are many others. ICN, I think, was an interesting example of a model that is equipped with the mechanism to work with its own outputs, seeking to achieve better performance, and also the one that we just went through, which is an approach that delivers explanations to the way machine learning classifiers behave by leveraging background knowledge. And I think personally that there remains much work to be done in this area, but there are some exciting results. Thank you.